get started. Thank you everyone for coming. This week we're welcoming Steve Raudenbush, who's a professor of sociology and the chairman on Committee of Education at the University of Chicago. He's a Harvard alum and is widely published in education, sociology, and wrote the book on hierarchical linear models. Today he's presenting work to us on estimands and estimators for multi-site randomized trials. Well,
thank you, Dana. That was blissfully short introduction. I appreciate it. So I want to talk about multi-site trials. I think they're really important, not only because they're done a lot, but because they're really interesting. We're having randomized experiments. There's going to be a random experiment in each of many sites. And so in some sense, you think it ought to be very simple and straightforward and obvious how to analyze the data. And I kind of thought that was true, and then the more I got into it, the more it seemed to be a little challenging, and particularly with the National Head Start Impact Study, which we're going to use as an example. So why are these so interesting? Well, a multi-site randomized trial is a fleet of randomized trials. Do I have this thing on? I think I do. So it's like a meta-analysis, right? It's like, you've seen these summaries of evidence where you have many replications of an experiment and you want to know on average, how well does this intervention work? How much does the effect vary? Why does it vary if it does vary, et cetera? So that's what a multi-site randomized trial is, except it's a little better in the sense that all the measures in every site are the same, so it's a little easier to work with. The heterogeneity of the sites, and by the way, the sites that I'm interested in are usually going to be things like schools, kids being randomly assigned to an intervention within schools, or teacher. In many cases, it's going to be a multi-level sort of thing where you have kids in classrooms. Classrooms are assigned at random to some new method of instruction, and that's happening within each of many schools or many school districts. So the sites are school districts or schools or hospitals or some other geographic areas like cities. And since 2002, the U.S. Institute for Education Sciences, which we never used to have randomized trials in education. And then all of a sudden, because we had this guy named Russ Whitehurst under the George W. Bush administration, founded this thing called the Institute for Education Sciences, we've had hundreds of randomized trials at the cost of some billions of dollars. It's a very exciting development in education research. The vast majority of those field trials are, in fact, multi-site trials, if for no other reason than you generally can't get a big enough sample in any one site, so you have the multi-site trials. But there are many of these also in medicine and social welfare and other areas. I'm particularly interested in the case where people are the unit of randomization today, although in many cases whole groups are randomized, and that's another area of interest I have. So here's a few examples of multi-site randomized trials. The National Head Start evaluation that I'm going to talk about. So you have a list of tens of thousands of Head Start centers all through the United States. The children, youth, and families people randomly drew a probability sample. We're going to just assume for simplicity here it's a simple random sample. It really wasn't, but to keep things simple, a random sample of 317 sites out of these many thousands of sites. Within each site, people applied to have their kids in Head Start, 3- and 4-year-olds, and there was a lottery to determine who would be offered a place in Head Start. So it's kind of like a researcher's dream, because you have a probability sample from a population of sites, and then within each site you've got literally random assignment of people. So it should be a terrific design. A really big contrast would be the Moving to Opportunity study. How many people know about the Moving to Opportunity study? This is in 5 cities. New York, Boston, Baltimore, LA, and Chicago. Low-income families, people actually living in housing projects, were randomly assigned to get a voucher to go to to be able to move to a non-poor neighborhood. So this is a contrast, because here we have 5 cities, randomization with 5 cities, and we can think of them, I'm going to think of them as more fixed. I mean, you really have 5 treatment effects, and you have to figure out you probably wouldn't think them as being randomly varying over a population of cities. It doesn't really make sense. So I'm not really going to talk, I'm just putting it up there because I want to delimiting what I'm going to talk about, what I'm not going to talk about. I'm not going to talk so much about that. But I do want to mention that Mike Sobel published a paper in 2006, or 7, I think it was, in the Journal of the American Statistical Association, noting that there were multiple housing projects within each city. And the randomization really it can be thought of as occurring. There's really a randomized experiment in a sense within each housing project. So I think that this really could have been, and in fact, ignoring that may have some negative consequences. So if we dug into that one a little deeper, it might become one of our cases where you have multiplicity of units of let's call them randomization pools. Okay. Then I'll talk about a couple of these others a little bit later. I just do want to mention the Tennessee class size study as an example with 3 levels, because here what we have is we have 79 schools, and within each school we're going to have large and small classes. Kids are randomly assigned to the classes, and then the teachers are also randomly assigned. But the real randomization that really counts here is the randomization of the teachers. So I'm going to think of this as children within schools, within classrooms. The classrooms are the teacher, within teachers, the teachers are randomly assigned, and this is occurring within each of many schools. And many of the IES-funded randomized trials, in fact, are are multi-site cluster randomized trials where as I said, classrooms are assigned within schools. So the program of research that I'm going to talk about, we're very interested in these multi-level sort of designs, of which there are many. Okay, so why are these interesting? Well, from a technical point of view, one way to think about it is, in causal inference, we usually think, if I'm a subject in a study and I'm assigned to treatment, you'll see how well I did under the treatment, but you'll never see how well I did under the control. Same thing for control. If I'm assigned to the control, you'll see how well I do there, but you wouldn't know how well I would have done under the treatment. And Paul Holland called this the fundamental problem of causal inference, is that each unit is observable, only one treatment. There's a missing data problem. We don't see both counterfactual outcomes. But if you think about the site as a unit, we actually observe the experimental and control outcomes. And we can do a lot with that. We can ask how variable are the impacts across these heterogeneous sites. In many of these cases, the sites are extremely heterogeneous. That's certainly true in the case of Head Start. And if you see very great heterogeneity in the sites and the kinds of people that make up the site, and you see, let's say, a large positive effect with no variation, it's telling you a lot about generalizability. It's telling you that there's a basis for theoretical generalizability, because people and sites vary in theoretically interesting ways, yet we see the same treatment effect. If we don't see a similar treatment effect, we see inconsistent treatment effects, then we can ask a bunch of other questions. We can ask how heterogeneous are these effects? How big are the biggest effects? Like, how well might this work in an optimal situation? If it's a positive effect on average, are there some places where it's really harmful and we have to worry about who might be harmed, kind of an adverse effect sort of situation? And we can ask questions about whether, for example, low-performing sites that have low control group means might have large effects, which would mean that the intervention is equalizing, or it could be the opposite. The sites that have the more advantaged kids actually gain more. So you can learn that, and then you can start doing modeling too. I'm not really interested in modeling moderator effects of different kinds of background variables. Here I'm just talking about what we can squeeze out of randomization. So there's a lot you can get out of these multi-site trials, a tremendous opportunity for learning. They're very expensive because they usually have very large samples. It's hard, costs a lot of money to recruit these sites. And yet, when you look across these hundreds of studies, what you usually see pretty much at the end of the day is a point estimate of the average effect and a standard error. That's pretty much what you see. So what's kind of motivating this project that I'm talking about here, this broader project that Dan Schwartz, my co-author in this, he's a student in biostatistics at Chicago, is to try to enrich the summaries of these evidence. And these trials, and Luke Miritrix has been involved in a big project that we've had with other people around the country. It's been a lot of fun to work with Luke and others on trying to enrich what we can learn from these studies. And it's kind of hard to get a hold of the data, but if you can get a hold of it, you can learn a lot more than has been learned so far. And maybe also learn a little bit more about how to design these things better too. I'll talk about that. So, so the challenge, so I said, well, it should be easy. I think Don Rubin at one point said that, a monkey could analyze a randomized experiment, so I think maybe we should hire some monkeys. They may be doing better than we are, because when you look at these things, they're not always analyzed quite the way you would hope. And so some of the challenges that turn out, it's true that if they were designed in a certain way, you could probably do it very easily. But when we actually look at the data from these, it's not necessarily that simple. So the first challenge is literally to define the population. Who are you targeting for inference? So two sort of obvious possible targets that I'll contrast here. One would be a population of sites or schools or hospitals. Really, it's not that there's an identifiable or particularly interesting population of people. It's really these organizations. You're really operating at an organizational level. Charter schools, I'll talk about that. Do charter schools work well? Are they working better than non-charter schools? How much does that effect vary? We're not necessarily talking about the population of all eligible kids for charter schools isn't well defined. It's not really the issue. It's in policy. So it could be the sites. In many cases, it isn't. It's actually the people. We really want to know on average how well does the effect work across a whole population of people. The sites are just sort of a nuisance, like maybe a bunch of hospitals are using some kind of new medication, and we don't really think the hospital, maybe it does, but we don't necessarily think the hospital matters that much. We really want to know how well does the population work and does that effect vary and so forth. So we have to define the population. Once we define the population, we have to define what are the quantities we're trying to estimate. And that's going to follow from the definition of the population. We'll often see a mismatch between the design and the estimates, so that when we actually see the way people organize the study, the sample sizes, et cetera, what we see is that the logical population that we want to really generalize to is out of sync with the way the sample was actually drawn. And one of the major reasons is that I think it's the case that in a lot of these studies, the actual size of the sample and actually even the propensity score, by which I mean the fraction of people in a site who are assigned at random to the treatment, those two things can plausibly vary endogenously. The designers of the study are not actually controlling the sample sizes and the probability of getting into the treatment group. I'll try to give you some examples of that. And when that happens, things get more complicated. When two things happen, when the design of the study is endogenous, okay, and when the treatment effects are heterogeneous, then things get more complicated. If the treatment effect is fixed, if you knew that a priori, then we could go back to the textbooks on experimental design and we just do this stuff automatically. It would be very straightforward. So that's the issue. And then if we have time, I'm going to say something about noncompliance. Oh, I'm from a place where people constantly interrupt, so if you feel like interrupting, I'm going to feel sad if you don't ever ask any questions. So I'll try to have a little enough waiting time so you can ask. Any questions so far? Just try to have a little waiting time here. And that never works, anyway. I'll say something provocative and then you'll ask. So in the Head Start study, so one of the reasons that the sample size and propensity score might be endogenous is so in each site, people are deciding whether to apply to get their kid into the Head Start. That might depend on whether there's an alternative center in that site, or there's an alternative. If your child is already going to go to a good center, maybe you wouldn't apply. Whereas in other centers, there might be this is the first opportunity, the only opportunity you ever have for your kid to go to a center. Otherwise, it's going to be staying home with you, and so you're more inclined to apply. So the number of people who apply could depend on these conditions that exist, and we don't even have a measure in the Head Start impact study of how many in each geographic area. What are the alternatives? And this comes up under noncompliance too, because what happens is. And Luke's got work that shows this, that if there's a contrast between if I have my kid in Head Start versus the counterfactual being staying at home with me, I don't have any education and, I love my child, but I don't have a terrific academic English vocabulary or whatever. So maybe I'm inclined to participate if I get the offer. But if there's another good center, then that would be the counterfactual. Maybe I'll just go to the other center. And we have some evidence that actually Head Start probably doesn't differ much in effectiveness from another center, but it probably does for, right? Am I saying this right, Luke? Luke, you can ask Luke about this. But so you have this potential endogeneity. In the charter school studies, same thing, and I've been doing a lot of work lately on charter schools. The number of people who apply to a charter school it could depend on, how close it is and how big the population is, but also how popular the school is. To what extent is it perceived as being a terrific school? And we have some pretty good evidence in Chicago that certain schools that have very good reputations draw a lot of applicants, which reduces the probability of winning the lottery. Okay? More people are applying. So the sample size and the propensity score are likely to be endogenous. Okay. Tennessee class size study. And there's a lot of non-compliance in the. I didn't mention. I only say just moving to opportunity. Just one of the major interesting facts there is people are offered a voucher to go and live in a much better neighborhood. Only 47% of the people actually use the voucher. People who are offered the voucher use the voucher. So that's non-compliance. In the charter schools, if you lose the lottery, usually you're put on a waiting list. So you might actually get into the school. That you're in the control group, you end up in the school, right? And some people who are offered the school don't go there. So that's non-compliance. Tennessee class size study, they wanted to have the small classes be about 16 or 15 or so, the large ones about 25. The realized contrast on average between large and small classes was more like 18 and 22. Something happened in those schools to equalize some compensatory things. I don't know, parents went in and pounded their fist on the desk and said, I don't want my kid in this large class, or something, because the realized contrast was smaller than it was supposed to be. So that's non-compliance, where you have a continuous compliance variable, which is the realized class size. Okay, is this making any sense? Is that okay so far? All right. So what our research program is that we seek consistent estimators of the average treatment effect in these multi-site trials, the variance of the treatment effects, the covariance between the control group mean and the treatment effect. That's this sort of equalization thing. If the control group mean is low, do we expect a higher impact or lower? And then, of course, we're very interested in site-specific treatment effects. In fact, what we'd really like to see, if we could see it, would be the entire distribution. Just look at the distribution of treatment effects. That would be everything. Then we'd know everything. If we had big enough sample and if everything were designed well, we would see that. But it's very hard to see that, and you'll see why in a few minutes. And we'd like to have these estimators for any well-defined population, even if the propensity scores and the sample sizes are endogenous. So that's the research program that I want to talk about. We've devised a way of sort of answering those questions that I'm going to tell you about, but not go into. I have an appendix of slides if anybody wants to see them. So we've developed a multi-level normal theory hierarchical linear model that has a control group mean and an experimental group mean, and they vary and they covary and all that stuff. And by introducing weights at any level, you can match the target population, and by using inverse probability of treatment weighting. So basically, we're sort of simulating a study in which the propensity scores are the same in every site. By doing those two things, we can get estimates of all those parameters that are consistent, meaning as I'm going to use J being the number of sites, goes to infinity, we're on target for the mean, the variance, the covariance, all of those things. And the nice thing is that, at least in a simple case with no covariance, but I think even with covariance, the resulting estimators don't really depend on a normality assumption. Even though we're using a normal theory log likelihood, it's a weighted log likelihood. It's simulating various balanced designs, and it's going to give us methods that are going to be consistent even if you don't have normality. So that broadens the array of things that we can study. So we can talk about that, but that wasn't what I was going to do today. I just want you to know that that's part of our program. What I want to talk about today is that these consistent estimators can be woefully inefficient. And what we end up with is a bias variance trade-off. And it's extremely acute in the Head Start study. Okay, that's what I want to focus on. And even more specifically, for today, just to keep things simple in the finite time we have, is that we're just going to be talking about estimating the average treatment effect, in fact, the average effect of being offered admission to offered a place in Head Start, the so-called intention to treat effect. You know what those things are? Intention to this is Harvard, causal inference. Everybody knows. Okay. If we have time, I'll say a little bit about some sort of logical interpretation problems with what's called the complier average causal effect under noncompliance. So those are the two things that we'll do. The data are from the Head Start impact study. Okay. So very simple idea. And everything we do is always built straight up out of potential outcomes. Everything grows out of the potential outcomes, and then all the assumptions follow from that. So in this case, so we have a T, so T is a 1 if child I in site J is assigned to treatment, and a 0 if not. And so capital Bij is the child-specific effect of being in we'll call it Head Start. So it's how well the child, what outcome we would see, and it's going to be a reading, actually, a reading outcome for that child if assigned to a Head Start, minus the reading outcome for the same child if assigned to a control group. That's going to be Bij. Okay? And so we're going to say that the average value within a site J, for site J, of these child-specific causal effects is going to be called beta sub j, and we're simply going to say that that beta sub j is equal to the overall average, theta, and that's going to be the focal parameter. Everything's going to be trying to get theta, plus some random effect b that's going to have a variance tau squared. Okay, that's very simple. I hope that's clear. Theta is our goal, but we still don't know what theta is. It's an expectation over what? For, what are we averaging over? What's our population? You see, it's not defined yet. So to try to make that explicit, I'm going to avoid integrals and talk about summations, even though we have infinite populations. It's going to be kind of weird. Luke usually asks me about that. It seems a little weird. It does seem a little weird. But one theta would be taking the expectation over sites of those site-specific beta j's. And so if j star is tens of thousands of sites, let's say 27,000 Head Start sites, I don't know what the number is, it's a huge number of sites in the population, it would just be the average, so beta j is the average treatment effect in site j, we would just, the mean of those means over the thousands of sites. That would be the estimand. Because why? Because we're interested in a population of sites. So that's what we would do. But if we were interested in a population of people and we knew the size, how many people were eligible for Head Start in site J? So NJ is the total number of kids who would be eligible for Head Start. Let's say if Head Start were expanded so that everybody had access to it, N sub J would be the number of people who would get it in site J, and we wanted to target theta sub persons. We would take the average over persons, and that would just be taking those beta J's. That would be the grand, right? That would be the grand mean over people of these person-specific things, right? Are you with me? That would be the same as just taking these and weighting by NJ. Okay, so these are two different things. These are both means, they're both thetas, but this is over a population of sites, this is a population of persons. Okay, they could be quite different depending on how much the NJs vary, right? Okay, so we got to make that decision. And we're going to focus today almost entirely on when we're looking at the population of sites, which is kind of like the meta-analysis idea of separate studies and what's the average effect across those studies. I'm not saying that the persons aren't interesting. The sites is a little more challenging, but often very interesting thing. So the data are going to be very simple. The data are just going to be beta hat for each site, which is going to be nothing more than the mean difference between the experimentals and controls in site J. Are you with me? Y bar 1 is J. That's the mean for the experimentals, people assigned to the Head Start. Y bar 0, the mean assigned to control. Difference is beta hat. That's unbiased for beta because we have randomization. And we're just going to say that now that equals the average, the overall mean effect, this random effect of that site-specific differences in the true effect plus the sampling error. That sampling error is going to have precision pj. Okay, so the variance of this, I should say really conditional on being in site J, no, this is the total variance, is equal to the variance in the population of the true effects. Okay, this is so crucial. Tau squared is the variance over the entire population in the true effects. Are you with me? Of the beta J's. whereas sigma squared over pj is the sampling variance of this estimator. And pj is just, pj is just the sample size times the t-bar, which is the fraction of people in the experimental group, times 1 minus t-bar. That makes sense? Okay? This pj is going to play a huge role. And we're going to assume, because in all the studies we've looked at, sigma squared is estimated with great precision. We're going to assume we know it. I'm just trying to keep this simple. We could have 2 different sigma squares, and maybe we should in some cases. I'm not going to do that here. It just makes life messier. And in fact, in Head Start, it really doesn't matter whether we assume that. So we're going to assume that we know sigma squared. So that means there are only 2 pieces of information we really need from each site. We need to know pj, what's the sampling precision of this estimate, and we need to know the estimate. That's it. Question over here? Yes?
Why did you say that looking at the sites as populations is more challenging than looking at?
Yeah, because the bias variance trade-off is going to turn out to be, at least in the case of Head Start, much more severe. Because it's going to turn out to be that the site estimator is going to be so potentially grossly inefficient, which is where I'm going to go, because you're not weighting by the number of people in each site. Yeah, so that's exactly where I'm going.
Before you change
Yeah.
line 1 and line 2, I can cancel the 2 beta j hats.
Yeah. I'm just trying to show that
But is bj equal to?
this is the estimator of this, and so I'm just trying to show that this is like the sampling error, if you will, with which beta hat j estimates beta, and it has variance sigma squared over p. This piece.
That theta plus bj minus beta j is 0. Is that true?
Did I do this wrong? No, I think this is right, because this is beta j, right? Theta plus bj is beta j, and then this is the difference. Yeah, right. Because, beta j is the population mean plus the random effect, and then that's the sampling error. That was the idea. Thanks for asking. Okay. Right, so are we okay? This is important. Make sure we're okay on this. Really want to make sure this is clear. Yeah.
You're assuming a common sigma square for treating the control group
Yeah.
in each site.
In many cases, not realistic. In this case, it works and it's simple, so I'm just going to assume it.
Yeah, but earlier you also mentioned.
By the way, if we have different sigma squares for the control group and the experimental group, it's not going to change anything about what I'm about to say. It's just the PJ is going to look a little different.
Yeah.
Okay.
That's just I saw in that earlier you said you're interested in the covariance between baseline outcomes
Yeah.
and treatment effects.
Right.
So
Between sites.
Between sites.
Between,
Okay.
but you're absolutely right. You're absolutely right. If there's heterogeneity of impact within sites, we would not expect the sigma squares to be the same. I totally agree with you on that. So I'm kind of hedging on this, but it turns out in Head Start, we get the same answer. And I just didn't want to have, the formulas get more complicated. I just didn't want to do that here. I don't think it's necessary. It doesn't really help. But you're raising a great point. Everybody see that? If you have a one-site study and people respond heterogeneously, the treatment effects vary, you can typically expect the heterogeneity of variance to arise from that. It doesn't have to, but it typically would happen. Because you're not going to be able to estimate how much the treatment effect varies within a site, because you don't see the potential outcomes for each person. But it will give rise to heterogeneity of variance. So we're just kind of hedging on that here, because we don't need. I don't want to go there today. That's not really what we're doing, and I don't need to. Okay, so we're just going to have 2 things that we're going to get out of each site: this contrast beta hat and this precision, this sampling precision. Everything's going to be based on that. Okay. So the unbiased estimator, I don't know how that thing, I just didn't even see that before. The unbiased estimator is just going to be, we're going to take every contrast, beta hat, j, and just add them up and divide by the number of sites in the study, j being the number of sites in the study, j star being in the population. I'm generally assuming that the sample size, in our case 317, is a tiny fraction of the many thousands of Head Start studies, which is really true in this case. So we're really in an infinite population kind of situation, but that's basically the unbiased estimator. Is it clear enough? That's an unbiased estimator. Even if in other words, even if the PJs are endogenous, and even if all that stuff happens, this is going to be consistent. So the problem is going to come for this estimator, and this is going to be why the sites is going to be the biggest problem, is going to be there are going to be 2 kinds of imbalance. We're going to have unequal ends per site, unequal sample size, and unequal propensity scores. And these can make the unbiased estimator, that's this thing right here, extremely inefficient, okay? So I'm going to borrow an idea from your dear colleague, one of the statisticians I love to talk to, Xiaoli Meng. This idea of self-inefficiency. So an estimator is self-inefficient if you can get a better result by throwing away data. Okay? And of course, no self-inefficient estimator can possibly be efficient, and I think it's pretty obvious that any efficient estimator must be self-efficient. And so what we see, now here are the sample sizes in Head Start. This is just unbelievable. Remember, now we're going to weight these sites equally. Here's just a histogram of sample sizes across 317 sites. 60 sites have fewer than 4, sample size smaller than 4. Okay? Something like 160, that's half the sites, have fewer than, I think it's 13 or 14, something like that. Okay? And then some of the sites are really big, 30, 40, 60, 80. This is real data. I mean, I didn't make this up to show how problematic things can get. This is the National Head Start Impact Study. And I even know why it was organized this way, because I had a barroom conversation with the people who did this. And they thought that they were working within a world where treatment effects are constant, and this turned out to be a good design. They didn't expect to get necessarily this much variation, but they didn't really care. They didn't care about all these many small sites, because they thought their models were all constant treatment effect models. It's because the treatment effect might be heterogeneous that this thing gets screwed up. Okay? Okay, so now this is going to take me a little while. Dan Schwartz came with this. I think this is a really cool idea. Okay, so imagine, just to get an intuition about why it might make a lot of sense to drop sites. Imagine you have 2 sites, one has 1,000 people and one has 2. And your estimator is the average of those 2 means, which is really going to have an effective sample size of more like 4 or 5 than 1,002. Are you with me? So throwing out the site with size 2 and just using the 1,000 cases in the site with 1, are you with me, would give you a much better estimate under one condition, which is that the 2 groups have the same true effect. So what we're saying is that if these tiny sites have the same effect as the big sites, we can throw them away and apply this estimator, wherever it was, this thing, and get a smaller standard error. So we can actually, if in other words, what we're really saying is if the precision of the estimator is uncorrelated with the effect size, we can gain a lot of efficiency by throwing away a lot of sites. And so what on the y-axis is, and it depends on how big the difference is between the impact of the sites you throw away and those you keep, right? If there's no difference, then you're down, oops, wait a minute, where's Dan's thing? You're down here. There's no difference between the sites that are thrown away and the sites that are kept, so there's no bias in throwing them away. Then this shows you how many sites you can remove to get an optimal estimator. You can remove 50% of the Head Start sites. You can throw them away. That's a lot of money to throw away, because the cost of sampling centers is a lot. If you've anybody ever done these studies, and you have to go to these places, and you have to talk people into participating in the experiment, and you've got to set up a randomization procedure and stuff, and you do that, and then you throw away 60% of them, you're probably wasting some huge fraction of the budget. So that's kind of a big problem. Throwing away 60% of data in order to get a better estimator, right? That's not good. That's not what we like to see. Now, however, if the difference between the sites you throw away on the average and the sites you keep is bigger, then you can afford to throw away fewer sites, and for the purpose of reducing the mean squared error. Are you with me? The mean squared error is the bias squared plus the variance. So you're reducing the variance by throwing sites away, but if the sites you throw away have a bigger effect or smaller than the sites you keep, you're introducing a bias, you square that. So you're paying a price. Are you with me? Okay, so in most extreme case, if the sites differed by 20 points, which is impossible, when I show, it's like 2 standard deviations or something. It's some huge difference. It's like 5 or 6 times bigger than any reliable estimate that we could get of for any site. But if it were that big, we couldn't throw any sites away. So what this graph basically says is that the estimator is self-inefficient because we can get a better result by throwing at least one site away, and probably you have to come down to where you think these are plausible differences, but we get down in here, you're throwing away maybe 20%. And again, if you think that the precision is orthogonal to the impact, then you benefit from throwing 50% of the sites away. Okay? Is it clear? That's.
But you could also use a different formula that accounts for the variability of the estimates.
Thank you. That's exactly where we're going to go. Thank you. Okay, exactly where we're going to go. So, remember I already put this up. Okay. So, but before we go there, I just want to, so here's where we're going to go. We can use some kind of precision weighting, right? We can give more weight to the sites that are estimated more precisely and dramatically reduce the standard error. But we would be introducing a bias if those precisions were correlated with the outcome, with the impact, okay? And so one of the things I tried to do is to figure out how plausible that these things really are informative. So I just said the sample size, let's just take the 317 sites and call and say that mu j is sort of the true underlying rate. Nj is kind of a random variable, but mu j is like the rate, sort of a rate parameter, and the variance of those is mu j. What we're really saying for each site, for a site, what we're really saying is that and we could say that the log of mu j has a mean of mu and a variance tau squared. And what we're really saying is here, under a Poisson model, in which every site has the same underlying true rate, maybe those NJs are just sort of popping up by chance. Are you with me? And we just totally reject that. I mean, the NJs are, the estimate of the variability between the sites and the NJs is huge. So a site that's the underlying true rate is 1.8 of a site that's 1 standard deviation above average is 1.8 times the average. So what I'm trying to say, I don't know if this makes sense to you, but I'm saying under a model, the Poisson model, constant rate, there's just noisy variability in the NJs, in which case we don't have to worry about the NJs. They're not correlated with anything, and we can get a huge bang for the buck when it comes to using the NJ as part of our precision weight, because it's not correlated. It can't be correlated with anything if it's just noise. But we reject that. Are you with me? Okay. So here's the propensity scores. They also vary hugely from 0.2 to 0.8 with a mean of 0.61. And so they also might be informative because they're part of the precision. Remember, the precision depends on the sample size and the fraction of people assigned to the treatment. Okay, so I did the same thing here. I said, suppose these sample propensity scores for each site there's an underlying true probability of phi, and the t bar j is just a binomial random variable given the phi, and then we would have this variance, a sampling variance, and then the logit of those things had a mean of mu and a variance tau squared. Now under this model, what we're saying is there's a mean mu and there's a variance of the true propensity scores of tau squared. Now we know that t bar j's vary, but that could be just noise. And actually, that's actually what we see here. There's absolutely no evidence, even though these things vary a lot, right? These propensity scores. We don't have to worry about any bias coming from these. There's no evidence that they vary except by chance. Okay, at least it seems like it's a very tight zero. So we really think that all of this variation is just noise. And if you looked at it, we call it a funnel plot of these things. There's no evidence that these things are heterogeneous. It's just that the t bar j's are randomly varying. You have all these sites that have such a small number of people that the t bar j's are just sort of randomly varying around. So we really don't have to worry about the t bar j's, but we do have to worry about the nj's. Okay, just think that's kind of a useful way of trying to diagnose whether precision weighting is going to cause us trouble or not. Okay. So how might we do what Carl suggests, which is how might we use the precisions to improve to reduce the variance, and what's going to happen if we do. So one way to do this is to use a site fixed effects model. So ordinary least squares regression with site fixed effects. Are you with me? Got 317 fixed effects. We've got 5,500 kids. We do the regression on the 5,500 kids, putting in 317 dummies or doing something that would be stupid. We've got better ways of doing it, but that's the basic idea. So we're only using the within site data, and what are we going to get? Well, what the site fixed effects actually is, when you do the ordinary least squares regression with 317 dummies, is really just a precision weighted average of those beta hats. It's just that precision, sampling precision pj times beta hat divided by the sum of those. So it's just using the pj's as a weight, the sampling. So every site has a beta hat j. We think that under fixed effects there's no heterogeneity. So we've got 317 unbiased estimators of the same parameter. The optimal estimator is to weight by precision, the inverse of variance. But there's a bias. If these PJs are correlated with these beta hat, with the BJ, the underlying true effects, we're going to get a bias. How big is that bias going to be? Everybody see why there's a bias? Because remember, the NJs are varying significantly. We're worried about the endogeneity. Maybe the number of people who apply is related to how effective the site is. So we're worried that there's a correlation between PJ and the true effect, BJ. It turns out to be the correlation between this ratio, precision divided by the average precision in BJ. Now, one of the things we've shown, and this is one of the results, I mean, this is the kind of thing that I get really excited about, but we'll see whether you do, which is that as j goes to infinity, this correlation is actually the covariance between a to j and bj, where a to j is the log of this ratio, pj over p tilde, which is the geometric mean. And we're going to assume normality here, but I'll explain why in a minute. So a to j is a standardized scale-free measure of how much imbalance there is in the data. I don't care. You can do anything with the outcome variable. You can multiply it by 50 and you can subtract and multiply or whatever you want to do with it. A to j will never change. A to j is a scale-free measure, and the sigma squared of eta is a global measure of how much variation there is across sites in precision. And it's the correlation between this scale-free thing, eta, or the covariance, I should say, and the true effect B that actually is the bias of the fixed effects estimator in large samples. Okay? So if sigma squared, now you can look at the sigma squares, and you can see how big they are, and you can even try to figure out how much of that is noise and so forth, and try to get some sense of how big this is likely to be. So that's kind of interesting. I don't know, is it clear? So we now have this measure of how much imbalance there is in the data, which is sigma squared eta, and how much bias is introduced by the fixed effects estimator. Okay? It's this covariance right here. It turns out we can do better than that by using a random coefficient model. Okay? And here's what happens. So the random coefficient model, and we're just for simplicity, and it's kind of a gross simplification, we're going to assume that the variability in the effect size is known, and we're going to weight by this reliability. Tau squared is how much the effects vary, divided by how much the estimates, the beta hats, vary. Okay? And so here's our random coefficient estimator of the grand mean. We're not weighting by PJ, we're weighting by this. Notice that if tau squared is 0, we have the fixed effects estimator, because this is it's going to be this is going to end up being PJ. Actually, it takes a little more algebra to show that if tau squared, but it's true that we'll be weighting by PJ if we think tau squared is 0. And the bias of the random coefficient model is the bias of the fixed effects estimator times 1 minus lambda. So the more reliably different the more reliably the sites differ in their true effect sizes, the bigger the gain you get from using the random coefficient model as opposed to the fixed effects model. It kind of goes counterintuitively. We're used to thinking that the fixed effects estimators are the sort of the least biased estimators. The random coefficient model has sort of a fishy reputation. But in fact, the random coefficient model will do better, and it will have smaller mean squared error. And showing that when we don't know tau is a little bit messy. But what's really happening here is that if there's great heterogeneity, if the sites vary a lot, the lambdas are going toward 1, and we're going toward the unweighted estimator. We're going toward the unbiased estimator. If there's very little reliability, then we're going towards the fixed effects estimator. So the random coefficient estimator will always be somewhere between that unbiased but inefficient average and the fixed effects estimator. And where you are on that spectrum is determined by how heterogeneous the effects are. This should make sense to you in the following sense. Imagine I've got 5 sites, and their samples are 20, 20, 20, 20, and 1,000. Well, if you thought the sites were all exchangeable, you'd probably want to wait. You'd sort of be inclined to weight the one with 1,000, very heavily. But if you thought the sites were extremely heterogeneous, you wouldn't want to give that much weight to the one with 1,000. I use the example, suppose the 1,000 was a school in Brooklyn. You're looking at the New York State, and the 1,000 is a huge school in Brooklyn, and the other are schools scattered around New York State. You wouldn't want to make the New York State estimate depend totally on what's happening in Brooklyn. So you wouldn't use the samples. You wouldn't weight by sample size. You'd weight by some reliability, and the optimal weighting scheme maybe in some sense. But this thing is kind of weird because it sort of varies between weighting by the number of people and weighting by and having no weights and having equal weights for each site, depending on how heterogeneous are. So it's kind of an interesting result. Yeah.
Are you talking about heterogeneity and treatment effects as correlated with the number of people in it, in terms of the size, or just heterogeneity in general?
The estimator, this estimator is operating as if there's no correlation. This is going to be a good estimator if there's no correlation. But this estimator is going to, it's going to have unit weight, equal weighting if lambda is 1, and it's going to have precision weighting if lambda moves towards 0. Okay. So, but it's also biased. It has a large sample bias. So what's the moral of the story? I'm going to give you the data from Head Start in a minute, but the unbiased estimator is potentially very noisy, and to the extent where we actually might benefit from throwing away up to half the sites, which is a drastic thing to do. The precision estimators have smaller variance but are not consistent if the precisions are correlated with the true impacts. The random coefficient estimator, if there is a bias, is going to always have I say unstrictly smaller, meaning that the bias of the random coefficient estimator is, for large sample size, is equal to or less than the bias of the fixed effects estimator. But it's inconsistent, meaning it's not a bias that goes away as you have more and more and more sites. It just stays there, and so it's sort of still a big problem. And you might say, well, why don't we just control for this eta j in the model? Just run a hierarchical model, a variance components model, where the estimate beta hat j is equal to the thing we want, which is theta, time plus the effect of this log precision thing. And then we have a variance component model. And it turns out what's very interesting, when you do that, you get back to this estimator, almost exactly, the sum of the beta hats over j. That actually controlling for this doesn't really buy you anything. In fact, when I do this, I get virtually the same estimator. I get this estimator, and the standard error doesn't go down. The reason is because we pay a price because we have to estimate alpha. So that doesn't really help us much. I kind of thought that would be the saving the game, way to solve everything. So here's what we get from Head Start. The unbiased but noisy estimator gives us an estimated effect of 4.86 with a standard error of 1.2. The fixed effects estimator gives us 5.7 with a standard error of about 1. The random coefficient is 5.6 with a standard error of 1.0. Now you might say, well, those are all pretty similar. But, and the reason they're similar is because they're all, I guess you would say, is because they're all sort of substantially bigger than their standard error. So we're not too worried. We can, so under all of these scenarios, we can conclude that there's an on average positive effect on reading of being assigned to Head Start. But, you know, if these were a little smaller but this far apart, you know, this could be the difference. You know, that's almost a 1 point difference. And it could be, it could change your belief if these standard errors were a little bit different. So, so anyway, we think that, you know, the randomized experiment is pretty robust to all of this stuff, but, you know, there's still a problem. And when you try to estimate the variance of the treatment effects, it's a bigger problem. Yeah.
What is the scale here? So is 6?
That's about 0.5 is about 20% of a standard deviation, roughly. Yeah.
Is this grade level?
Yeah, these are 3 and 4 year olds. It's on a standardized Woodcock-Johnson reading test. Yeah, yeah. So we really, you know, and the thing is, when we estimate the bias of, well, I call it FERC. Really, this is the random coefficient model. We get this estimate. The problem is we don't have a precise estimate of the bias. It just doesn't get us anywhere to estimate the bias. We can't really correct it because there's a big confidence interval around the bias. So what's really happening with Head Start, it's really a design issue, I think. If you choose your population carefully and you design in accord, you know, that's a good thing. But if you have sample sizes that are highly variable, mini, small, and endogenous, you end up in this kind of weird thing where a consistent estimator may be noisy to the point of being self-inefficient. A precision weighting may produce a bias, an inconsistency. And in some sense, I guess it seems to us, at least, that in retrospect, the Head Start study could have been much better designed. Maybe there were cost factors driving the fact that there's a lot more, I'm sure there were, people in some sites than others. But there's a cost that's also imposed by having such heterogeneity of precisions and having so many small sites. And it gets worse when you try to estimate the complier average causal effect, because that's harder to estimate than the ITT effect. So I'd like to stop for, let me tell you what else I got here. I'd like to talk a little bit about, or we could talk a little bit about complier average causal effect. So in Head Start, winning the lottery and therefore being assigned to the Head Start increases the probability of your actually being in Head Start by about 75%, which is pretty good, actually. So it's 75. The compliance rate we say is 0.75. But it's not 1.0, and we'd like to know how we can estimate the average of the complier average causal effects. And I'd like to say something about that, but I'm extremely disinclined to do that until I hear more from you, your questions, comments, and whatever, because you guys are giving me the kind of stony faces here, and I don't know whether that means what I'm saying is just transparently obvious or whether you're completely lost. So why don't we see, what do you think so far? What are you, thoughts, comments, questions?
So in general, the random effect estimator has both smaller bias and a smaller variance.
Yes, right. And as the heterogeneity gets big relative to the sampling precision, it converges to the unbiased estimator. But as the heterogeneity goes to 0, it converges with the fixed effects estimator. So it's kind of a nice, it puts us in a nice continuum. But the fact that it has a bias that doesn't go away, you know, it's inconsistent, is a big problem. That means if we have enough sites, you know, we're zeroing in on the wrong quantity. That's not a good thing.
How do you operationalize it? Do you fit a multi-level model, get an estimate for your tau, and then calculate those weights?
Yes. So for the simplicity of presentation, I'm assuming that the taus are known, which is far from the truth. And we have, we're working on a paper where we show what happens when you're actually estimating, and it's tricky because it's an iterative solution where the average, the estimate of the average effect depends on your belief about the variance, and the estimate of the variance depends upon your belief about the average effect. But generally, these same principles hold, at least in large samples. We would expect smaller bias with the random coefficient model, even when we have to estimate the tau, and smaller mean squared error, expected mean squared error. Yeah. But that doesn't mean it's a good estimator, because it's inconsistent. Are you with me? So that's the problem. Yeah.
And one way to think about what it's doing is it's basically taking advantage. If you don't think you have much treatment effect variation, then you don't care so much about your unbiased estimator because your bias can't be that big, I guess is what.
Well, yeah, I mean, of course, yes, exactly. If the heterogeneity, if the variability in the treatment effect is 0, all of these things give you the same, they're all unbiased. There's no
So take a
problem.
look.
And you don't have to worry about whether you're going to sites or you're going to people, the estimands are the same, and the estimators, any reasonable estimator is going to be unbiased, but then the efficiency. So then the random coefficient model then comes to save the day and says, no, that's not right. Then the fixed effects estimator, which is equal to basically converges, the random effects converge. So what I'm trying to say is, let me be a little more clear. If there's no variance in the treatment effect, actually, the precision-weighted estimators are better. But the unweighted estimator is bad. Right. Yeah.
So we're in the world of simple random samples, right? But I'm curious about how your conclusions about which estimators we should and should not use change if we're looking at something like a match pair experiment or a perfectly like a really well stratified experiment. Like you made the claim that that the bias was a function of eta, which is basically balance in the experiment, right? So can we change things about the consistency if we can really get really tight balance?
Right. Now, the thing is, but let's say you had a matched pairs experiment. Suppose you matched the study, well, wait a minute. I got to be clear here. Here we're talking about matching people. Matching people.
Yeah, sorry, I guess you can think about matching people or
Uh,
matching.
Right. Well,
Yeah,
the problem is, when you match people, you're still going to come up with a beta hat J that's going to be a summary for site J. No matter how you do the covariance with people, you use covariance adjustment, you use matching, whatever you use, you're going to have a beta hat J, which is going to be your best estimate of the treatment effect in site J. It's going to have a precision. All of the same problems are going to come at you.
Unless all the precisions are the same.
Unless all the precision, except, okay, yeah. Now that gets us into the thing I didn't talk about. If we're generalizing to a population of people, and the true sizes vary, then the balanced design is going to hurt you. Then you would like to have a self-weighting design. It's a cost issue aside, where the sample size is proportional to the population size. So, and then what that would mean in Head Start. So think about, it's really interesting what that means in Head Start. Remember how different the sample sizes are? That's kind of like throwing out data. Because if all of those sites that have a sample of 2 are weighted by 2, and the sample that has 80 is weighted by 80, then you have 40 times the weight. Selfish inefficiency is sort of a drastic idea. We're going to throw away data. Well, what's that mean? We're assigning weights of 0 to half the cases. Well, now we're assigning weights of 2 relative to 80. You see what I'm saying? So when you weight by sample size, let's say you thought you wanted, let's say you're the kind of person you think, I want every child to count equally in Head Start. I'm still basically throwing away about 30% of the data because you're giving such small weight to those many, many small sites that you're basically almost throwing, not quite, but almost throwing them away. Yeah, so that's, and I mean, maybe this is one of the most important experiments that's been done in the last 15 or 20 years. It's a really important experiment. I mean, at least in the child welfare business. And, it doesn't seem like what we see, the realized design is kind of defensible on any particular, unless unless that's the cheapest thing to do and we think we have a constant treatment effect. Then we should use a precision, we should use a fixed effects model and we're home, and we're done. But if we think there's heterogeneity, the whole thing falls apart. Chris?
Could you talk about, from a policy perspective, why you think your estimate is the right thing to be looking at? Is it
Well,
data distribution of the
yeah.
thing?
Well, first of all, I mean, yeah. What does it mean to say that Head Start is effective on average? You know, if you think, well, like, is a typical Head Start center a good place to be? Then you're kind of thinking it the way I'm doing it. If you're saying, well, there's some population of kids who might be eligible for Head Start, and in that population of kids, what's the average benefit of being in Head Start? Then, you know, you would go to a person weighted. In our paper, we do both. Here, I'm only doing this one. I think I think in the charter school case, I think it's pretty clear that people are more interested in schools. They don't think that there's a well-defined population of kids here. It's just they want to know if charter schools are working better. You know,
I guess I'm asking why an average is supposed to.
Well, no, an average, no.
The distribution.
Oh, yeah, no, our whole project is all, I'm sorry about that. Our whole project is getting the distribution. That's what we're interested in. Or, you know, the moments of that, the mean, the variance, and this covariance between the control group mean. And, you know, we're really interested, and we're interested in site-specific estimates, maybe some empirical Bayes or Bayes estimates of those things. We're interested in all of that stuff. I just think it's kind of interesting that the easiest thing to do, and the thing that most people want to do, which is to simply estimate the average ITT effect, is a little trickier than you might see. And I do want to say that if you're estimating the variance of the treatment effects, everything is harder. The unweighted estimators are much worse than the precision-weighted estimators. So, yeah, no, I mean, I'm with you on that, totally, yeah. I mean, and also, so Howard Bloom always tells me, you're interested in the average, you're interested in the variance of the treatment effects, but what does that mean when you're generalizing to a population of people? Well, really what you're saying is, so people vary in their treatment effects. Part of that variation is within sites, we can't estimate it. The other part is estimated is between sites, we can estimate that. So it's the component of between person variance, people's heterogeneity and impact that lies between sites. I think that's still interesting. Yeah, Andrew.
So I really liked your figure 3, and I just want to make sure I understood it. I'm not sure you have to click all the way back there.
It's easy enough.
But to what extent did that depend on the particular distribution of sizes in Head Start?
It is this is for Head Start.
That's what
This
I
is
meant.
absolutely for Head Start.
Right.
And, you know, maybe this is like one of the worst ones you'll ever see, because
Right, and so
Head Start
that's-
is really pretty extreme.
Exactly, and that's
Yeah.
sort of the question. I think you ended up addressing it, but I just wanted to make sure, like, how does this depend on the imbalance, right? I think you had a log normal in there somewhere, and so is that for the sample sizes? And so at what point does the skew of this distribution or the location of this distribution make you say, this isn't that much of an issue anymore? Does that make sense? Like, I think this might have been your balance question, right? As the sample, to what extent, at which point might we not be worried about this as much as the sample sizes increase and there are fewer 2s and 3s?
Yeah, so in a paper which I can send you that we're still revising, we also we study the welfare to work demonstration, which has 59 sites and like 1,000 people per site. And there's all of the estimators work very well.
Right.
There's almost no, maybe you could throw away one site. There's almost no self-efficiency problem in the welfare to work. So this kind of footprint is kind of like study specific. But I think it's useful in the sense it's a way to see the bias variance trade-off that you might see in any study. And it doesn't take a lot of information to estimate this. All you really need is to know what your sample sizes are. And then you're kind of you're saying plausibly how big are the mean differences.
It's a great plot.
Yeah, it's a nice plot, but I think it's also useful to do that little Poisson analysis,
Yeah.
and that little, because if basically you know, so here's the famous example with Poisson, right? You know, people in London during World War II were being bombed the Nazis were shooting rockets over. And some neighborhoods were hit like 5 or 6 times, right? And other neighborhoods maybe once or not at all. And so some people thought maybe Hitler hated their neighborhood. And so, you know, were they really targeting certain neighborhoods? The technology they had suggests that they couldn't possibly have been doing that. All they were doing was lobbing rockets across. And so the model that fit best was a straight Poisson model, fit perfectly, where every neighborhood had the same event rate. Okay, that just what we see, so literally the people who had the 5 hits were unlucky. That's all there was to it. And you can do the same thing with sample sizes here. Do the sample sizes just vary randomly and use a 2-level Poisson model for that? Estimate the over-dispersion parameter if it's 0.0000, then use the precision estimator. So that's kind of a nice diagnosis. And that's what we saw with the propensity scores. They were all over the place, but it's utterly consistent with a pure chance model. There's no significant heterogeneity in the probabilities that give rise to those T-bar J's being all over the place. So we're trying to give people some tools to look at these data sets, and maybe the tools could help you. You know, a lot of times, I think in some cases we would absolutely go immediately for the precision-weighted estimator because there's just no basis to think that there's any association with the precisions. But in other cases, we probably would have to go with consistency, which is a basic statistical principle that you want consistent estimates. You don't want to have estimators that have a bias that stays with you no matter how big the sample gets. That's just not what you want. Yeah.
Yeah, quick design question, because I don't know not much about Head Start. Were all the interventions at the same time?
Yes.
Okay.
Yeah.
Because no one ever talks about temporal heterogeneity.
Right. Right.
Of effects, and to the extent that the interventions vary over time, and you have both potentially going on.
Exactly.
Right. And
Yeah.
That's true of a fair number of experiments, particularly those that are attempting to replicate.
Right. Now I will say
Like for the domestic violence experiments.
Right. So okay,
Job
Job
one
Corps.
in Minneapolis, and then they do 5 more.
Right.
So you have multiple sites, but then they are sequenced in time.
Okay, let's go to
then
Job
how
Corps.
do you add that in?
Exactly. Let's go to Job Corps, which is another one of the most important big randomized experiments in social welfare that we've had. Huge study. Here's how they did it in Job Corps. As people came in and slots were available, they randomly assigned people. But slots so there's the number of people coming in, and this occurs over a long period of time. Slots become available when one of 2 things happens. Either a person drops out of the program or they graduate. So the sites that have a lot of dropouts have high propensity scores. But also the sites that graduate people fast have high propensity scores. So it's kind of an interesting, you know, the good sites presumably are graduating a lot of people. The bad sites are sort of forcing people out. And this is rolling over time. And then the number of people applying is depending on who knows what. It could be the local unemployment rate. That's another very important thing. You know, people might be going in if they can't find a job. There's a lot of endogenous reasons, or maybe they think the program is good, or there's just a high-risk group of people, whatever. So the NJs and the propensity scores are kind of changing over time. And people are coming into this program at rates that are being endogenously determined by this dynamic. So, you know, I think we have to get away. The machinery that we've been working with comes to us from agricultural experimentation. You know, where people, which is beautiful. I mean, it's R.A. Fisher, fantastic stuff, Kemp Thorne and so forth. All the experimental design texts, they all come from that, where, you know, the researcher has a lot of control, although not total control, because you can put the fertilizer on and it can rain and still spill over. So we won't go there. But, right? So I think your point is well taken. I think Job Corps would be particularly vulnerable to that criticism. Conditions are changing, the program, you know, and all of these other dynamics are occurring. I'm not sure if that helps answer. Yeah, Ken.
You had a model, 2 models, the random and the fixed effects one.
Right.
And the effects seem pretty similar, so this made me wonder.
Yeah.
Is there some reason you couldn't use like a Hausman test to see if there's a significant difference between the 2 and thereby maybe justify the
Well,
effects?
yeah, I don't think that, okay, so here's a funny thing about this. Here's a funny thing about this. see if I can find it. Sorry. Yeah, it's this one. It turns out that I can put any number greater than 0 for tau squared between 0 and infinity in this formula and get smaller bias than the fixed effects. I can literally, if I put infinity in there, then I have the unweighted estimator. Okay, if I have 0, I have the fixed effects estimator. So any number greater than 0 is going to make these lambdas become constant at 1. So if I put infinity in there, I'm going to basically get the unbiased estimator, but it's not going to be very efficient. If I put 0 in, I'm going to get the fixed effects estimator. So the idea here would be that tau squared, the number that you should put in, should reflect how heterogeneous the treatment effects are. And that should, in some sense, be optimal, but it's only optimal if these things are not correlated. Okay, so what would happen is the bias of the random coefficient estimator would, if lambda's 1, it goes to 0. If lambda 0, it goes to the fixed effects estimator. This is approximate, but there's an error term here, but it's not very big. Okay. So by the way, Hausmann was so we need to go back and revisit Hausmann, Mundlock, Madala, all of those people in the late 70s. They were all working with constant treatment effect models. We need to go back and look at them again, because you see the models that they were using, it was a random intercept model, not a random coefficient model. That's first of all. We have a fixed intercept random coefficient model. Okay, does that help a little bit? Essentially, that's what we're doing, because we're only looking at contrasts. But I want to say something about that. This has been an enormously influential literature. Have you guys read this stuff? Back 78, 80. It's the literature that makes people say the fixed effects estimator is better than the random effects estimator unless you have a Hausmann test. You've heard that? Most economists sort of, that's what they eat for breakfast, during econometrics, that kind of stuff. Let's think about how that model might fit into this, our paradigm might be useful. In their case, the treatment of the sites were people. And the people were observed under an experimental and control condition. Okay? Now, there are also some other people who never got the treatment, but I don't want to quite go there. It makes it a little more complicated. If you have attrition, then some people are going to have more observations than others. So the attrition can cause a bias. If you have a heterogeneous treatment effect, then weighting by precision, i.e. using a fixed effects estimator, would presumably introduce a bias. Using a fixed effects estimator, because you're weighting by precisions. If the precisions are based on how much non-attrition there was, and attrition is related to the outcome, then you would have a bias. That didn't come up in that literature because those guys their models had constant treatment effects. Okay, so that's one of the next things I really want to do is I want to go back and look at that literature, and I want to look at interventions, not necessarily, might be, if you're a psychologist, maybe we randomly assign within people or we randomly assign the order, it's a within subjects experiment, but maybe they're not randomized. And by the way, this whole thing, I've been trying to figure out how to do this when you have randomization. When you don't have randomization, everything that we're saying here I think still applies, except it's more complicated because now we don't know what the propensity scores are. We have to estimate them. Okay, but in this literature where we have these within subject treatments, and we're generalizing typically to a population of people, meaning we want to weight each one of those, our estimand is to weight every person equally, but yet people have different amounts of data, and you're weighting by precision, you can actually have a bias. This would to some extent upend that literature, I believe.
So I just want to go back to the design question to
Yeah.
see how this kind of an imbalance came about in Head Start.
Yeah.
And does that relate to your target of inference framework, which is there's a target of inference which is sites, and then there's a target of inference which is kids.
Right.
Was this the treatment was the kids, right? So it's not truly a quote like the Chicago style multi-level design study. Is that why this kind of an imbalance came about?
Well, But even what I was trying to say is, even if your target is people, having a lot of sites with 2 people doesn't do much good because those sites are getting they're not having any influence. I mean, it's wasting a lot of money, even if your sites, because you're giving almost no weight to these tiny sites. I think so. I won't say who, but yes, I did have a barroom conversation with people when they were designing this study, and what they were saying was that one thing they were learning about multi-level data was that if you're interested in an average across sites, particularly a person-specific average, having many small sites could be an optimally good design. Because if you have a small number of sites, you have a big standard error. So let's put all our money into having a huge number of sites with very few people. And then, of course, some of the sites were able to, I don't know why some of the sites have 80, 60, 50, I don't know about that. But by design, this was a study in which the number of people per site was small and the number of sites was big. But it turned out to be many sites had tiny sample sizes, and they varied. But I know that the people who were saying that were thinking, this is going to be a great design if, and they were really thinking of a constant treatment effect model when they said that. And they were also thinking that what we really want, what's going to be interesting, are site-level moderators. So let's say one set of sites uses the Perry preschool curriculum, which is high scope, right? The high scope, and then other ones don't. We want to know whether high scope works better. So does high scope have bigger? So when you do those kind of things, you want a lot of sites. So they thought, we're going to put all our money into sites, and we're going to have tiny sample sizes within sites because that's the best estimate, yes, under a constant treatment effect model.
But the randomization of the treatment was still at the kid level within sites.
It was within each site. There was a randomization within each
So
site.
the moderator was the framework that led them to this having multiple sites.
Yeah, because if you look at the Head Start literature, a lot of it's driven by how do we make Head Start better? And so better curricula, better teachers, smaller class sizes, a lot of I didn't get into that, but that's where a lot of this, the policy, because you're asking about the policy issues with Head Start. Really, a lot of people, of course, there's always people who want to, is it good or bad? And then if it's bad, we're going to cut it. But Head Start's very hard to get rid of. So if you say, well, we know we're going to keep it, then why have this study? To make it better, right? So to make it better, so if we're going to make it better, then really we're thinking about sites as the unit. How do we make the sites work better? That was really and then if I gave a lecture on how to estimate the moderating effect of a treatment, let's say all the high scope sites, maybe we should do that versus the non-high scope, everything I'm saying, then we know sites are the unit, I think. And then everything I'm saying would be true. Would still be true because you'd have exactly the same trade-offs. Yeah. Right. Yeah.
So you talked a lot about how it's problematic to assume you have a constant treatment effect, but
Right.
how do you know you don't? Or is that a question of the design? Like you wouldn't expect to see a constant treatment effect here, or the theory, or is there some kind of Q test, or
Yeah, there's a test.
Yeah.
But I mean, sort of a priori, I'm sort of assuming, there's going to be heterogeneity.
Right.
So in human populations, and sites are going to be heterogeneous, people are heterogeneous. So, and by the way, Howard Bloom, Mike Weiss, and Natalia Verbitsky have a paper, I think it's in the Journal of Research on Educational Effectiveness, where they apply this kind of framework to like 10 or 15 of the studies funded by IES. And generally, if there's anything happening, there's also some heterogeneity. I mean, there's some studies in which there's no average treatment effect and there's no heterogeneity. It's sort of like it should go into the education department has this what works clearinghouse. It should go into the list of what never works clearinghouse because and the average is 0 and the variance is 0.
Right.
And that's good to know, right? That's
So
generalizable.
It's more that the assumption should always be.
It's sort of like, well, you kind of a priori think that you wouldn't want to go in to most of these with the assumption strongly held that it was constant. And then the question is, how much information is in the data about that hypothesis? And it turns out in Head Start, and we have some graphical ways of showing this, Head Start doesn't have a lot of good information to tell us whether there is heterogeneity. The confidence interval, the best confidence interval we come up with, I don't know what you came up with, Luke, if you did the ITTs. Howard Bloom says there's a lot of heterogeneity, but our confidence interval goes from almost 0 to a pretty big number.
Over tau.
Yeah.
I believe it, because you
Yeah.
have such noise on all of your sites.
Yeah, and the multiplicity of tiny sites is really hurting us for that Q statistic.
Which is written up, the Q statistic and stuff, the Weiss paper that you mentioned has a very nice discussion of how to do the testing for heterogeneity.
Yeah, and it's a normal theory-based test that's the problem, but basically you test the hypothesis for every real number greater than 0 and you reject, and the region of acceptance is the confidence interval. You know, it's just something you just beat the data to death with the machine until until you get this confidence interval. But it's a good thing to do, and you see these confidence intervals are a lot bigger. And I hate to say it, but certainly with the data we've been looking at, it's pretty hard to estimate the correlation between the control group mean and the impact. Our confidence intervals are big on that. So, yeah.
That's
What was the reference?
all the time that we have today, but I believe.
Oh,
Steve will
I'll
be
tell you
around,
after.
If you
Yeah.
have any further questions. Thank you, everybody, for coming. Let's give a round of applause.